Alternative hypothesis testing.
Good job.
Again.
Welcome to the lecture on null hypothesis testing. This is going to be one of the most important lectures of the entire semester, and if there is one thing that you really take into the next QBA course, null hypothesis testing is definitely the concept that needs to be thoroughly understood before moving on. So, null hypothesis testing. First of all, a hypothesis is a statement about a population parameter that you need to verify. So, in other words, I am making a statement based on whatever information I have, saying I believe this about the population, and then I need to use sample data to verify it. So, it begins with a hypothesis statement about a population parameter. And then, such as, for instance, I believe that the average cost of a kitchen remodel is $20,000. Well, I can believe that it's $20,000, but unless I have data to back that up, it's pretty much useless. So that's what a hypothesis is for, is to be able to say, hey, this is a statement that I need to verify. Another example is, you could say the average speed of a car passing milepost 150 at the West Virginia Turnpike is 68 miles per hour. Once again, this is a great statement, but unless you take a sample and say, hey, this is what it actually is with a certain amount of confidence, we don't really know for certain what it's going to be. So there is a 6-step procedure of hypothesis testing, and you'll notice the 6-step procedure down at the bottom. And we're going to go through every single one of these steps. We're not going to go through it in depth. That's what the subsequent lectures are for. But this is just going to be a brief overview of what hypothesis testing looks like. So once again, the purpose of hypothesis testing is to say, hey, this is what we believe about the population. Let's take a sample and let's determine, is what we believe about the population, is it actually true? So hypothesis testing, once again, is based on sample evidence and probability theory to determine whether or not the hypothesis is a reasonable statement, whether or not we have enough proof, enough of a reason to believe that what we're saying is actually true. So step one. Step one is to state the null hypothesis and the alternative hypothesis. So these two terms are definitely probably new terms. So a null hypothesis basically states that the sample and the population are equal, or that both populations are equal. In other words, null means that there is no difference. Null means no difference. No difference between what is being examined and the actual population, or what's being examined in one group and what is occurring in the other group. So once again, null, just when you think of null, think of no, as in no difference. So alternative hypothesis is when you're attempting to demonstrate that that a sample is different from another sample, or that a population is different from another population, or a sample is different from a population. And so an alternative hypothesis says, hey, this is what we believe about this sample and how it is different from the population. It's the alternative to the null. It is essentially the opposite of the null hypothesis. So once again, we're still in step one with stating the null and alternative hypothesis. Once again, the null hypothesis is a statement about the value of a population parameter developed for the purpose of testing numerical evidence. So a null hypothesis is a statement. It's not rejected unless our sample data provides convincing enough evidence that it's false. And so we're testing this. We are testing to see, is the null hypothesis false? We start every single hypothesis testing believing that the sample is equal to the population, or that the sample is equal to the other sample. It's kind of like, innocent until proven guilty. You need to believe that one sample is the same as the population until you demonstrate it otherwise. That's what we're doing right now. So failing to reject the null, so let's take a look at the alternative hypothesis. The alternative hypothesis is the statement that is accepted if sample data provides sufficient enough evidence that the null hypothesis is false. So we are either going to reject the null hypothesis or we are going to fail to reject the null hypothesis. But when we fail to reject the null hypothesis, it doesn't prove that the alternative hypothesis is true. Okay, or sorry, better yet, when we fail to reject the null hypothesis, it doesn't say that the null hypothesis is true. It just means that we failed to disprove the null hypothesis. The alternative hypothesis is what we're going to conclude if we reject the null hypothesis. We'll turn to the alternative hypothesis only if the data suggests that the null hypothesis is untrue. So we're testing the null hypothesis, and if we can demonstrate that the null hypothesis is not true, then we're going to adhere to the alternative. Now with the null hypothesis, this is really important. It often includes the equal sign, the less than or equal sign, or the greater than or equal sign, where with the alternative hypothesis, it never includes the equal sign. Even if you truly believe that the sample is equal to the population, still the alternative hypothesis is never going to include the equal sign. That would still be this weird concoction of the null hypothesis. And so it often includes, the not equals to, the less than, or the greater than sign. So let's get an example. We're going to look at this sample right here, the null hypothesis. We've got some information about starting salaries. This table includes the mean starting salaries of all business majors from a sample of 75 students. So there's a sample of 75 management information system students, and then this is all actually the population data for all the rest of them, the economic, logistics and supply chain, so on and so forth. So, let's just assume that there's 75 of each of these, if you will. So, and then the population of all majors combined is at the bottom of the table. You'll see all majors is $54,365. That is the population mean. The population mean is $54,365. So with the null hypothesis, here's our example of the null hypothesis. The null hypothesis says that the point estimate of the starting salary of graduates, so in other words, the population starting salary of graduates with bachelor's degrees in MIS is equal to the average starting salary of graduates with bachelor's degrees in business. So that's the null hypothesis. Notice that it says that they're equal. The average starting salary of graduates with bachelor's degrees in MIS is equal to the average starting salary of graduates with bachelor's degrees in business. The alternative hypothesis is going to basically say the opposite. It's going to say the average starting salary of graduates with bachelor's degrees in MIS is not equal to the average starting salary of graduates with bachelor's degrees in business. So that concludes the first step. Now we are on to the second step. So we stated the null and alternative hypothesis. Now we're going to look at the level of significance. There's not one level of significance that's applied to every single test. It's up to the researcher to decide on the level of significance before formulating any sort of decision rule or collecting the sample. You need to make sure that you decide what the level of significance is prior to taking any samples. It is a risk if you take rejecting the null hypothesis when it's really true. So let's take a look at this. So you're going to select a level of significance, like I said, and it's signified by the Greek letter alpha. And once again, we always assume that this sample is equal to the population before testing, which is what we said earlier. We assume that the null hypothesis is true. And this is also often referred to as the level of risk. Rejecting the null hypothesis when the null hypothesis is actually true. And we'll get into that in just a second. So the level of significance is the probability of rejecting the null hypothesis when it's true. Okay. In other words, when the sample is actually equal to the population, you still reject the null hypothesis. So like I said, with what we do, we normally use the level of significance of 0.05 for consumer research. For other types of research, you might use, 0.01 or zero point 0.1 for political polling, things like that. But you're going to use, for our purposes, you're going to use a 0.05 normally, because with consumer research, that's a pretty acceptable alpha level. So there is inherent error that's possible simply to do with the fact that we're not dealing with the entire population. Because we're not dealing with the entire population, there's always a chance that we're wrong. So type 1 error is rejecting the null hypothesis when the null hypothesis is actually true. So it's rejecting the thought that there is no difference when in actuality there is a difference. And we signify that with the Greek letter alpha. Then type 2 error is failing to reject the null hypothesis when the null hypothesis is false. So in other words, you're saying you're failing to reject the null hypothesis when in fact there really is a difference between the sample and the population. So, but you say that there's no difference between the two, and this is signified with the Greek letter beta. So this is a contingency table, or some sort of that you look at the researcher when the null hypothesis is true and when the null hypothesis is false. For some people, you like to have a visual of this of what's a correct decision. The researcher does not reject the null hypothesis when the null hypothesis is true. That's the correct decision. If you reject the null hypothesis when the null hypothesis is true, that's type 1 error. When you do not reject the null hypothesis when the null hypothesis is false, that's type 2 error. And when you reject the null hypothesis when the null hypothesis is false, that is also the correct decision, which is in the bottom right-hand corner. So, in the present example that we have specifically dealing with the majors, with the MIS majors, we're going to use an alpha of 0.05. So let's put this hypothesis back together. So all that we're doing now is we're just adding alpha to the exact same statement, and we're saying, okay, before we ever collect any data, we're going to make sure that we are going to adhere to an alpha, or we're going to say that we're okay with a risk level of being wrong. We're okay with a risk level of rejecting the whole null hypothesis, once again, rejecting the null hypothesis, the risk level of type 1 error when the null hypothesis is true. So let's go back. So we are okay with a 0.05 risk level of that. Okay, and so we've got the null hypothesis and the alternative hypothesis right there. And you notice all that I did, it's the same exact thing. It's just we put in alpha. Next, we're now on to step 3 of the process. So step 3, we are going to decide what test statistic we're going to use. Now, there's a lot of different types of test statistics, and these are just the 3 that we're going to deal with in this class. We're going to deal with Z, we're going to deal with T, and we're going to deal with chi-squared. More specifically, right now, we are only dealing with T and Z. In hypothesis testing, when we're testing for the mean, when the standard deviation is known, we're going to use the Z. And when the standard deviation is unknown, or the population standard deviation is unknown, we're going to use the T distribution. And so the test statistic is just a value that we're using to test whether or not we should reject or fail to reject the null hypothesis. So we can determine, basically look at the distance between the average of the sample and the average of the mean, or the population mean. So the mean of the sample and the mean of the population, and see if the mean of the sample is enough standard deviations away from the mean of the population for it to be statistically significant. So, what statistics should we use? We've got right here, we've got a z-score. If you look in this right-hand column over here, you're going to see the 95% confidence interval. The Z is up at the top, and then the T is down at the bottom. And this is really important because if you notice with the Z scores, the limits, these are the confidence intervals, right? The confidence interval for the management information systems and the confidence interval for all majors. The confidence interval for the MIS majors, when you look at the Z-score compared to the T-score, you notice that the confidence interval is actually more precise with the Z-score. And the reason why is because we're dealing with the population standard deviation, therefore we're able to be a little bit more precise. But when you look down at the T-score, we are dealing with the T-score with a sample standard deviation. So it should say sample standard deviation instead of population. And because of that, it's actually going to be a little bit wider, the confidence interval. And so when we're dealing with that, the level of significance is going to be a bit more varied or a little bit more conservative as compared to dealing with the Z distribution. But in this particular situation, we're going to be using the Z distribution, the Z test statistic. So with that, we are going to put just a little bit more information in here. We're going to say, okay, we've got a standard deviation of 15,400. We've got a sample size of 75. We've got an alpha of 0.05. And we just keep on adding a little bit more information. And we're going to say, hey, you know what? We're going to use a Z statistic. And because we're going to use a Z statistic, a Z test statistic, something that I don't actually have written in here, and I really should. The Z test statistic is going to make it so that we are going to have a critical value of 1.96 for a two-tailed test. And so we're actually going to get to that in step 4. Okay. So in step 4 of the process, we've got the critical values. The critical values are essentially the dividing point in the normal distribution or in the T distribution that says, you know, if the mean of the sample is beyond this critical value, then we are going to reject the null hypothesis. If it is within this critical value, we're going to fail to reject the null hypothesis. So we're going to formulate the decision rule, and so with this decision rule, this is a rule that you're going to stick to. It's a statement of specific conditions under which the null hypothesis is rejected and considered conditions under which it's not rejected. And so it's really important to do this before you ever take any sort of data. And we're going to get into that in just a minute. Okay, so the sampling distribution of the statistic Z follows a normal distribution. So with an alpha of 0.05, which I'm going to show this to you right here, with an alpha of 0.05 with a two-tailed test, we're going to have the critical values of negative 1.96 and 1.96. And so if I were to calculate so what you're seeing right here, this distribution, this normal distribution, what it is it is the normal distribution of the population. So right now we're taking a sample and we're comparing a sample mean to a population. And we're saying, okay, we want to know, does the mean of the sample, does it fall inside, you know, where there's 95%? Probability, does it fall inside of there, or does it fall outside of the 95%? Does it fall below the negative 1.96, or does it fall above the positive 1.96? If it falls in one of those two areas, we are going to reject the null hypothesis. But if it falls above 1.96 but below if it falls above negative 1.96 but below 1.96, we are going to fail to reject the null hypothesis. And so there's a 5% chance. Notice basically a 2.5% chance on the left and a 2.5% chance on the right, but there's a 5% chance that we are going to reject the null hypothesis when the null hypothesis is actually true. And we're okay with that because a 5% chance, you know, that's still pretty decent probability that we're going to be correct. We basically have a 95% chance that we're right. Okay. So the values of 1.96 plus or minus is what divides the regions between the rejection and the not rejection. So the sample has a mean and uses the same standard deviation as the population. This is really important, this one statement right here. There's going to be situations where your sample does not have the same standard deviation, but right now we're assuming that the sample does have the exact same or very close to the same standard deviation as the population. And because of that, we're able to compare them very easily. But if the mean, with consideration for the standard deviation, falls within the confidence interval, we fail to reject the null. So this right here is a visual representation of when we would fail to reject the null. You notice we're going to say that the blue distribution right here, this blue distribution is going to signify our sample, where the purple distribution is going to signify our population. And you notice that the blue distribution, that the mean falls within the confidence interval of the 95% confidence interval of the population. And in this situation, we would fail to reject the null hypothesis. And then on the next one, you'll notice that the mean of the sample right here, the mean of the sample falls well outside the population confidence interval. And so because it falls well outside the population confidence interval, we're going to reject the null hypothesis. So in our example, what we're going to say is our decision rule is we are going to fail to reject the null hypothesis if the z-score, and this is really important here, like you can literally write it just like this. We are going to fail to reject the null hypothesis if the z-score is above negative 1.96, above or equal to negative 1.96, or less than or equal to positive 1.96. Conversely, we are going to reject the null hypothesis if z is less than negative 1.96, or if 1.96 is less than z. So that is our decision rule. So our z-score results. Right here, I want you guys to see that these are all of the z-score results. If I were to compare every single one of these majors to the average or to the population, the right-hand column is the z-score results for all of them. So anything that is beyond plus or minus 1.96 is going to be considered statistically significant. Now, there are only two majors that are actually statistically significant. In other words, there are only two majors that we can say are significantly different enough from the mean that we can say they are in fact different. And that is, if you look at management information systems up at the top, it says that it's 2.96 standard deviations or 2.97 standard deviations above the mean. And what was our threshold again? The threshold was 1.96. Anything above 1.96 is going to be considered statistically significantly different. On the other end of the spectrum, hospitality management is 3.23 or 3.24 standard deviations below the mean. Once again, it is well beyond that negative 1.96 threshold. And because of that, we're able to say that management information systems is statistically significantly different, and that hospitality management is also statistically significantly different. So, which I just jumped ahead a little bit, but now we're making a decision. Which I just kind of did the decision. Sorry, I kind of jumped ahead a little bit, but first we need to select a sample. I already told you guys, we selected a sample. The sample was a sample of 75, and we computed the value of the test statistic. So if you look right here, we took a sample of 75, we got the mean, and we found the value of the test statistic. I guess I just kind of jumped ahead there. So compare the value of the test statistic to the critical value, then make the decision regarding the null hypothesis. Okay, so right here, the z-value of MIS majors compared to all other majors is 2.96. So this is what you should be writing, right? So the z-value of 2.97 it is greater than the critical value of 1.96. Because of this, because the MIS major is greater than the critical value of 1.96, we reject the null hypothesis, and we conclude with a 5% chance of being wrong, or a 5% chance of type 1 error, that we are concluding that that MIS majors are different than the average business major, or that the starting salary is different. So finally, we're going to interpret the results. Okay. So what can we say or report based on the results of the test statistic? Now, when we do this, we're not just reporting the z-value. So what I did in the previous slide, it was just giving you the straight up, this is what's true about the z-value. This is not just what we're doing. We are giving real insight. Okay, like for instance, include the mean, include the standard deviation, the p-value, other statistics, and give me some information that says, okay, are they different and how are they different? Why do we care? Okay, so here, this is a really good example of a write-up. Okay, we can conclude that the average starting salary, or the mean starting salary of $59,642 for MIS majors is statistically significantly different than the average graduate with a business degree with an with a standard deviation of 15,400. So 15,400, that's the standard deviation. That's still quite a large standard deviation, and it's hard to necessarily tell right away that it is different. So that's why it's really important to run this test. So MIS starting salaries are on average $5,277 higher than the average business graduate. Another thing that's really good, which I didn't put it in here yet because we haven't covered it, is to put the p-value. So the p-value is essentially, if you look at that z statistic, the z statistic was what was it? Let me take a look at this. The z statistic was 2.96759. So you find the z statistic of 2.7695, and then you return the corresponding probability from the z table. And reporting that in here as well is a really good thing because it gives a better understanding of how significant it actually is. So this is what you really should be writing and with giving your insight, and so that way somebody can understand. Now I'm going to give you just one more quick visual. This right here, if you notice the red distribution in the center, the red distribution in the center is essentially saying, hey, here are all the business, or better yet, this is the distribution considering all the business majors together. And so you'll notice that all the rest of the business majors are also compared to, the mean of everyone. And so on the right-hand side, you have management information systems. On the left-hand side, you've got hospitality management, and then you've got all the rest of them somewhere in between here. But there's only one that we really care about right now. And the only one that we're testing is the management information systems compared to the business majors. And you'll notice that the mean of the management information systems is well above the mean of, or the confidence interval of the average business major. And because of that, that's why we're able to conclude that the average starting salary of management information systems students or graduates is statistically significantly higher than the average starting salary of all business students. So that concludes this lecture. Hope this was beneficial to you, and feel free to watch, pause, do whatever you need.